Hello, let's continue with medium voltage networks and systems. Medium voltage networks play a crucial role in power distribution. Electricity is generated from power plants. From there, it moves through high voltage transmissions networks over a long distance. Closer to consumer energy is transferred to medium and low voltage distribution networks and delivered regionally. About half of the total electricity cost is linked to distribution. For this reason, the structure and reliability of distribution networks requires strong technical and economical justification. Medium voltage networks usually operate in radial configuration. Power flow from one supply point towards consumer along feeders. This structure is simple and cost-effective. When designing a medium voltage networks, you must consider nominal voltage level, substation configuration, reserve supply options, network lengths, and branching. These factors influence reliability, power quality, and investment cost. Distribution networks are divided by consumer type. Industrial network supply largest facilities. These are often international networks within the factories. And urban network supply dense loads with many cable lines. Rural network supply dispersed loads. They often include long overhead lines and fewer consumers per kilometer. Voltage selection depends on load density and distance in Estonia. In Estonia, common medium voltage levels are 6 kV and 10 kV. Voltage levels of 15 kV and 20 kV are used in some regions. The 35 kV level connects larger substations. There is a gradual shift toward lower voltage levels in distribution. For example, instead of supplying 10 kV over long distance, more compact 20 kV systems within shorter feeders are used. Every voltage decision affects short circuit level, equipment rating, losses, investment cost. Network configuration also links directly to supply reliability. Consumers are grouped based on required supply security. Critical consumers include hospitals and facilities with complex technological processes. These require high reliability and often dual supplies. Less critical consumers can tolerate short interruptions. Now consider how feeder length affects protection. In radial feeder supply from one side, fault current decreases as distance from the source increases. This directly influences protection settings. Instantaneous overcurrent protection clears faults without internal delays. Typical operating time ranges from 5 to 100 milliseconds. The pickup current must be set above the maximum fault current at the far of the end of the protection zone. The rule is ES equals safety factor multiplied by the maximum short circuit current at the limit of the protection zones. The safety factor is typically between 1.1 and 1.5. If the feeder is supplied from both ends, both relays must use the same pickup settings. The setting is based on the higher consumption from either side. In the middle section, protection zones overlap and both relays may operate instantaneously. Protection is fast but has limited reach. It works best on radial feeders. To achieve selectivity across the network, time delay overcurrent protection is used. In independent time delay protection, each upstream relay has a longer delay than the downstream relay. Coordination follows a simple rule. Operating time of stage E equals operating time of stage J minus 1 plus the selectivity margin. This selectivity margin must cover relay operating time. This ensures the relay closest to the fault operates first. Upstream devices act as backup. The drawback is longer fault clearing time near the source. To solve this, network combine instantaneous protection with the time delay protection. Close faults are cleared immediately, distant faults are cleared with the coordinated delay. In practice, this two-stage scheme balances speed and selectivity. For example, in rural feeders within 20 km overhead line, a surge circuit near the substation produces high current and is cleared instantly. A fault at the far end produces lower current. It may require time delay protection to the main coordination within the downstream devices. In urban cable networks, higher short circuit levels allow broader instantaneous zones. In industrial systems, dual supply and higher fault currents require careful coordination between both ends of the feeder. Medium voltage networks design always connect three aspects: topology, voltage level, protection coordination. And your goal as an engineer is to ensure reliability with the minimum cost while maintaining safety and selectivity. Every feeder length, every voltage choice, and every relay settings influences system performance. This is why medium voltage distribution engineering requires both technical precision and economical reasoning. Medium voltage networks form the link between high voltage transmission and low voltage consumers. At the top level, we have the 110 kW transmission networks. This is the regional backbone. From there, power flows into primary substations. In those substations, voltage is transformed from 110 kW down to 35 kW and 20 kW, 15, 10 kW or 6 kW, depending on the regional standards. The 35 kW level often acts as an intermediate level. It connects large area substations and distribution power further to the medium voltage feeders. The medium voltage networks then distributes power to intermediate substations and so on. Distribution substations. From distribution substations, voltage is stepped down to lower voltage for final consumers. This layer structure ensures controlled voltage transformation, manageable short circuit levels, stepwise distribution of the power. Now let's examine some consumer supply categories. Consumers are divided into three groups based on supply reliability requirements. First group, consumers require the highest reliability. This includes hospital, large industry processes, critical infrastructure. They must be supplied from two independent sources. It may cause a third backup. In many cases, a third backup sources is added. The sources must be electrically independent. A fault in one must not affect the other. Second group, consumers also require high reliability, but short interruptions are acceptable. These consumers are supplied from two independent feeders. If the main supply fails, an automatic transfer switch connects the backup source. This switching may take seconds. Industrial facilities often use this scheme. Third group consumers include residential buildings and small consumer loads. They are supplied from the single source. If the fault occurs, supply is restored after repair or manual switching. Now consider how this structure appears in practice. In a typical region, a 110 kV transmission line feeds a primary substation. The substation steps voltage down to 20 kV and several 20 kV feeders supply distribution substations. Each distribution substation supplies a low voltage network. If the feeder supplies a hospital, two independent 20 kV feeders are installed. In the feeder supplies a residential area, usually one feeder is sufficient. This structure balances cost and reliability. Supplying every consumer from two independent sources would be technically possible, but economically unjustified. About half of the electricity cost is linked to the distribution infrastructure. Every additional feeder, breaks, and transformers increase investments. Therefore, network design always follows a clear principle: match reliability level to the consumer importance. In industrial zones, ring or dual feeder structures are common. In rural areas, long radial feeders dominate because load density is low and the investment must be controlled. As an engineer, you must understand voltage level hierarchy, substation's role in the transformation, feeder structure, consumer reliability categories. All those elements from one coordinated system, medium voltage network structure, is not random. It reflects technical constraints, economic limits, and reliability requirements. Electrical networks configuration describes how branches and nodes are interconnected. Based on the structure, distribution networks are divided into four main types: radial networks, branch radial networks, ring networks, and mesh networks. Each configuration has clear advantages and disadvantages. Your task as an engineer is to select a structure that matches reliability, cost, and protection requirements. First, the radial network. In the radial network, power flows in one direction from the source to consumers. Each feeder supplies its loads without alternative paths. The advantage is simple and clear structure, easy protection coordination, low investment cost, and disadvantages are low supply reliability. A single fault disconnects all downstream consumers. Radial networks are widely used in rural medium voltage system. Long overhead lines and low load density makes simplicity more important than redundancy. Second, the ring network. In a ring network, feeders form a closed loop. Consumers can be supplied from two directions. The advantage is higher supply reliability, better voltage stability, lower power losses compared to long radial lines. Disadvantages are more complex protection, more complex operation and switching. In practice, many medium voltage ring networks operate in open loop mode. One switching point remains normally open. This keeps protection simple while allowing quick restoration after the fault. For example, in the urban 20 kW cable network, feeders are built as a ring. Under normal operation, one point is open. If a fault occurs, operators isolate the faulty section and close the open point to restore supply from the other side. The third, the mesh network. A mesh network contains multiple closed loops. Power can flow through several parallel paths. The advantage is very high supply reliability, excellent voltage stability, minimal power losses. Disadvantages are complex and expensive protection. Complex operation and coordination. Mesh structure are typically a transmission system and in the high reliability industrial networks. At voltage levels 110 kV and above, meshed operation is common. In medium voltage distribution, fully meshed networks are rare due to the protection complexity and cost. An important practical detail concerns switching points. In medium voltage distribution networks, special switching location allows feeders to be sectionized. These switching points divide the networks into smaller sections. During the normal operation, the networks may functionally radial. During the fault operation, isolate only the damaged section and restore supply to the healthy sections. In Estonia, 35 kV networks often operate in closed configuration. Lower voltage networks such as 10 and 20 kV often operate radially as open rings. The key engineering principle is clear. Higher reliability requires higher investments and a more complex protection. If you design rural feeders with a small load, radial configuration is economically justified. If you design city center networks with the hospitals and commercial centers, ring configuration provides better continuity of supply. If you design transmission backbone mesh configuration, ensure maximum stability. Network configuration directly influences faulty current levels, relay coordination, voltage profile, operational flexibility, protection design, switching theory, and others. You must always align the chosen network structure with those parameters. There is no universal best configuration. The optimal solution depends on the load density, required reliability, and a livable budget. Closed network schemes and ring structures allow supply reservation. In those systems, reserve switching automation is used. This automation restores power to the region without waiting for repair crews. Key elements that enable fast restoration are sectionizing, substations, switching points, remote controls, disconnectors. These elements allow you to isolate faulty section and re-energize healthy sections quickly. In contrast, non-reserved radial networks are mainly used for consumers who accept lower reliability. Branch radial networks are common in rural areas, load density is low, and electricity is transmitted over long distances. Closed loop or two-sided supply networks are used in the both urban and rural system when higher reliability is required. Now let's examine distribution function from another perspective. There are two main approaches to the distribution power between medium voltage and low voltage. First approach extends distribution more on the low voltage side. In this case, the medium voltage feeder supplies a substation, and from there low voltage feeders distribute power over the consumers. This approach reduces medium voltage infrastructure cost. However, low voltage feeders become long, voltage drops increase. Losses increase, power quality decrease. Second approach is extend distribution more on the medium voltage side. In this case, medium voltage feeders are extended deeper into the load area. More distribution substations are installed closer to the consumer. This leads to short low voltage feeders, lower voltage drops, power losses. However, this investment cost increased due to more substation and medium voltage equipments. In Estonian currently designed practice limits low voltage feeders length approximately 600 meters. This rule improves voltage quality and reduces losses, especially in rural areas. Let's look at the practical examples. In sparsely populated rural areas, one 10 kV feeder may run several kilometers. Small distribution substations are installed along the line. Each substation supplies short 0.4 kV feeders to the nearby houses. This structure balances cost and voltage quality. In a dense urban area, a 10 kV or 20 kV cable network forms a ring. Multiple compact substations are installed within short distance. Low voltage feeders are very short. They ensure stable voltage and low technical losses. The choice between more medium voltage distribution and more low voltage distribution, the effects are investment cost, technical losses, voltage stability, reliability. As an engineer, you must evaluate load density, distance, and require quality of the supply. If you extend low voltage too far, voltage drops become unacceptable. If you extend medium voltage too far, infrastructure cost rises significantly. Optimal design requires balance. Network configuration, switching capability, feeders, lengths, and voltage must be worked together. Now let's compare two typical medium voltage supply structures. Both examples show 110 kV transmission networks at the top and the 10 kV distribution level below. The difference lies in how the medium voltage system is organized. In the first schema, the 10 kV network is interconnected between substations. Power can flow feeder substations. Feeders are close connected. If one transformer or feeder fails, another path can be supplied part of the load. This structure increases operation flexibilities. The advantage is higher reliability, possibility of load transfer between substations, better utilization of transformer capacity. However, protection becomes more complex. Short circuit levels increase due to multiple in-feed sources. Relay coordinates require careful calculation. This type of structure is common in urban cable networks, where the load density is high and supply continuity is critical. In the second scheme, each 110 kV to 10 kV transformer supplies its own radial 10 kV feeder. There are no cross connections between medium voltage sections. Each transformer operates independently. The advantage is simple structure, easier protection coordination, low short circuit levels, lower investment cost, and so on. The main disadvantage is lower flexibility. If one transformer fails, the entire load disconnects unless manual switching is available. This structure is typical in smaller towns or rural areas. Now consider practical operation. In the interconnected schemes, if transformer T1 trips, operators can transfer part of its load to transformer T2. This can be made in medium voltage switching in the power stations. In the independent radial schema, if transformer T1 trips, all connected feeders lose supply until the transformer is restored or temporary switching is arranged. From a protection point of view, interconnected systems require direction over current protection, more advanced coordination, careful circuit analysis. Radial systems often use non-directional overcurrent protection, simple time coordination. The choice between the structures depends on load density. In density centers with hospitals and data centers, interconnected 10 kV systems are justified. In rural regions with the dispersed load, independent radial feeders are economically justified. As an engineer, you must evaluate not only technical performance but also economic impact. High reliability always increases cost. The goal is to select a structure that matches the raw importance of the supply load while keeping protection manageable and operationally safe. Now examine busbar system in large primary substations. When the substation supplies many medium voltage feeders, the internal busbar arrangement becomes critical for reliability. One common solution is two busbar system with two transformers. In this schema, each transformer feeders its own busbar section. Feeders are divided between the two sections. A sectionized breaker connects the busbar. Under normal operation, the sectionized breaker remains open. Both busbar sections operate independently. If one transformer fails, reserve automation closes the sectionizing breaker. The healthy transformer supplies the both sections. This arrangement provides high reliability, operational flexibility, possibility of maintaining without total shutdown. In very large substations or more complex schemes with the 4 busbar sections and 3 transformers may be used. This ensures that even if one transformer is out of service, sufficient capacity remaining available. However, such schemes increase cost and protection complexity. For this reason, more economical solution is often selected. In the typical 2-section system within 2 transformers normally operate separately. The bus coupler remains open, automatic transfer is enabled. If voltage on one busbar disappears, the reserve switching automation connects the sections. Feeders on the de-energized sections receive power from the healthy transformers. Now let's consider how low medium voltage feeders are arranged. In common distribution scheme is the medium voltage ring feeder in this section. Feeders leaves the substation, they form a ring through the several switching substations. One switching point is the ring is normally opened. This open point ensures radial operation under normal condition. Protection remains simple because the power flows in one direction. If the fault occurs, the fault section is isolated using load breaker switches or disconnectors. The normally open point is closed. Supply is restored from the opposite direction. This structure combines radial protection simplicity. Ring network reliability. In the diagram, closed switching are marked with one symbol and open switch with the other. This indicates which sections are energized and which point remain normally open. In practice, this schema is widely used in 10 kW and 20 kW networks. For example, in a city district, several compact substations are connected in the 20 kW ring. Under normal operation, one switching substation keeps the rings open. If the cable fault occurs, only the damaged cable section is isolated. Consumers beyond the fault are resupplied from the opposite side. This minimizes outage area and duration. From an engineering perspective, this solution balances investment cost, protection complexity, operation reliability. Busbar configuration and substation feeders configuration in the network must be worked together. If the substation provides sectionized busbars with automatic transfer and the feeder operates in the open ring configuration, the entire medium voltage system achieves high reliability without extensive protection complexity. Your main design task is to ensure clear normal operating state, define switching sequence during the faults, proper relay coordination, and transformer capacity under reserve condition. Only when these elements are coordinated does the medium voltage system operate safely and reliably. Now we focus in detail on the medium voltage ring feeder scheme. The diagram shows us a typical 10 kW feeder leaving the primary substations. From the busbar, several feeders connect to the switching substations. These substations are interconnected, forming a ring. In the figure, closed switches are marked with a single line symbol. Open switches are marked with a double line symbol. Under normal operation, one switching point in the ring remains open. This creates radial operation. Power flows in one direction only. Protection coordination remains simple. Non-directional overcurrent relays are sufficient in the most cases. Why keep the ring open? Because the closed loop operation must increase short circuit current and require directional protection. It would also complicate coordination between relays. Open ring comparison gives you reliability without excessive protection complexity. Now consider a fault scenario. If the cable fault occurs between two switching substation, protection at the substation detects overcurrent. The feeder circuit breaks, trips. The fault section is identified and isolated using load breaker switches. After isolation, the normal open point in the ring is closed. Healthy sections are resupplied from the opposite direction. Only the damaged cable section remains without power. This significantly reduces outage area and duration. The schema is widely used in 10 kW and 20 kW urban networks. In rural areas, similar logic applies, but the feeders are longer and switching points may be less automated. Key technical aspects you must evaluate. Short circuit current at the different points in the ring. Voltage drop along the feeders. Load transfer capability during reserve operation. Transformers capability under a single transformer operation. For example, if one feeder normally carries 5 MV and transformer's rating is 10, during reserve operation it may need to supply 8 to 9. You must verify firmware limits and voltage regulations. Another important aspect is switching device selection. In the medium voltage ring networks, you typically use load breaker switches for sectionizing. Circuit breakers at the primary substation, load breaker switches can interrupt load current but not high short circuit current. Therefore, fault clearing is done by the circuit breakers at the substation. Automation improves performance. Modern systems use remote control switching devices and fault indicators. When a fault occurs, fault passage indicates the fault direction. Control systems identify the faulty section. Switching sequences are executed quickly. This reduces restoration time to the hours to the minutes. The medium voltage ring feeder schema provides a balanced solution: radial protection, simplicity, fast restoration capability, and moderate investment cost. As an engineer, your task is to ensure that normal operation configuration is clearly defined. Reserve switching sequence in the predefined protection settings match both normal and reserve states. Equipment ratings supply temporarily overload during the transfer. When these conditions are satisfied, the medium voltage ring feeder becomes a robust and efficient distribution solution. Now we examine the typical medium voltage feeder in more detail. From one primary substation, the number of outgoing medium voltage feeders can reach several dozen. Each feeder supplies a definite geographical area. The feeder may consider only one branch. However, in practice, most feeders include several branches. Branching usually takes place in pole-mounted substation or compact switching substations. These locations are equipped with disconnectors, load breaker switches. Those devices allow planned or emergency change of network configuration. You can sectionize the feeder, you can isolate the faulty section. You can disconnect part of the network from maintenance without shutting down the entire feeder. The endpoint of the medium voltage feeder is usually a distribution substation. In that substation, voltage is transformed from 10 kV to 20 kV down to 0.4 kV to low voltage consumers. Let us analyze the structure shown on the diagram. Closed switches are marked with the single line symbol, open switches are marked with the double line symbol. Under normal condition, the feeder operates radially. Power flows from the substation outwards through the branches to the distribution transformers. If a fault occurs in one branch, the substation circuit breaker trips. The faulty section is identified, switches are opened to isolate the damaged line segments. After isolation, healthy branches can re-energize. This minimizes outage area. Branching provides operational flexibility. For example, if one branch supplies an industrial consumer and another supplies residential load, you can disconnect only the industrial branch during the maintenance. Another key function is branching is load balancing. If feeder loads become uneven, you can rearrange switching points to redistribute load between adjacent feeders. For engineer perspective, you must evaluate maximum load current in each branch, short circuit current at each switching point, voltage drop along the longest branch, selectivity of protection device. In long rural feeders, voltage drop can become critical. If 10 kW feeder extends over several kilometers, the far end voltage must remain within acceptable limits under the peak loads. This often determines maximum branch length, location of the distribution substation, conduct cross-section. In urban cable feeders, branches lengths are shortened, but the load density is higher. Short circuit currents are also higher. This affects protection settings and equipment ratings. The medium voltage feeder is not only a line, it's a structured system with the defense switching points, branching logic and protection coordination. Your design must ensure clear radial operation under normal conditions. Defines sectionizing points, fast fault isolation, safe maintenance capabilities. When properly designed, a branch medium voltage feeder provides reliability, flexibility, and economic efficiency. Now examine the feeder interconnection and two feeder schemas. Feeder interconnection allows you to change network configuration when needed. In practice, the most common structure is single ring schema. In this arrangement, two substations are connected by one medium voltage ring. Feeders operate in open loop mode under normal conditions. However, in the areas with the higher reliability requirements, a true feeder schema is used. In this configuration, two primary substations are interconnected. Each substation supplies multiple feeders. Feeders are interconnected through switching points. Normally, certain switches remain open to maintain radial operation. If necessary, you can change the location of the open points. This allows load transfer between feeders, isolation of the faulty section, supply restoration from the alternative sources. Compared to the purely radial network, this schema provides higher operational reliability. Let us look at how this works in practice. Under normal operation, each feeder supplies its own load area. Interconnected points between feeders remain open. If a fault occurs one feeder, the faulty section is isolated. The open point between feeders is closed. Part of the load is transferred to the neighboring feeders. Only the damaged section remains without supply. This flexibility is not available in simple radial networks. It's a strictly radial system. There is no alternative supply path. All downstream consumers lose power until repair is complete. In the true feeder schema, the open point can be moved depending on the load condition. For example, during peak loads, you may position the open point to balance transformer loading. During the maintenance, you may shift the open point to maintain supply to critical consumers. From protection perspective, the system still operates radially and any given time. This keeps protection relatively simple. Non-directional overcurrent relays can often be used. However, you must consider maximum load current during the transfer, short circuit current variation depending on the supply direction, transformer capacity in reserve mode. For example, if two 20 kW feeders are interconnected and one transformer fails, the remaining transformer must temporarily carry increased load. You must verify thermal rating, voltage regulation, protection settings under the new power flow conditions. In urban areas with dense load, the two feeder schema significantly improves continuity of supply. In rural areas, it may use selectivity for important consumers. The key engineering principle is flexibility. By providing interconnection between feeders, you create multiple operation states without increasing protection, complexity, and the level of faulty meshes. The two feeder medium voltage schema achieve important reliability, operation flexibility, and control investment. Your task is to define normal switching state, emergency switching sequence, protection coordination for all configuration. Only within these aspects are analyzed together does the system operate safely and efficiently. Now we analyze reliability and protection in the two feeder medium voltage schema. Supply reliability is higher in the two feeder configuration. Consumers can receive power from the same primary substation through the different busbar section. From two different primary substations in the more advanced configuration, even four substations may In more advanced configurations, even four substations may participate, so the load are supplied from the nearest available source. Sectionizing points are located at the distribution substation, a switching station at interconnection between neighboring feeders. Distribution substations often have two transformers. This allows additional reserve capacity at a low voltage level. The main advantage of this configuration is clear. High supply reliability. The main disadvantage is also clear. High investment cost of transformers and switching devices. Therefore, the network configuration is always selected based on consumer type, required reliability level, economical constraints, and technical condition. Now let's move to the protection of the medium voltage feeders. Medium voltage feeders are typically equipped with relay protection operating through the circuit breaker. Protection type vary depending on the voltage level and network configuration. Feeder sectionizing is performed at the primary substations using circuit breakers or disconnectors, along the feeders using load breaker switches for grounding during the maintenance. In the medium voltage networks, portable earthing is also applied when necessary. Creating switching points and sectionizing location allows isolation of the faulty feeder segments, isolation of the transformers from the network, and safe maintenance of the work. Circuit breakers are remote controlled. Load breaker switches may also be motor operated. In recently constructed or reconstructed substations, most switching devices supply remote operation. In older substations without remote control, switching is performed by operational crews. From a system design perspective, you must ensure safe isolation procedures, clear switching sequence during the faults, reliable grounding during the maintenance, and coordination between relay protection and switching devices. For example, if a feeder breaks trips to the overcurrent, operators must verify faulty location before reclosing. If the maintenance is required on a feeder section, it must be disconnected, isolated from all possible supply sources. Grounded securely, reliability does not depend only on the network topology, it also depends on the protection performance, switching device reliability. Now we compare urban and rural medium voltage networks. The main task of the medium voltage network is clear. It transfers electricity from a primary substation to distribution substations, where the voltage is transformed to low voltage and delivered to final customers. However, the structure of the network depends strongly on the load density and consumer distribution. Urban and rural networks differ significantly. Let's start with the load density. In urban areas, load density is typically higher than 1 megawatt per square kilometer. In rural areas, load density is often below 100 kilowatts per square kilometer. This difference alone determines many design choices. Now consider the number of consumers per distribution transformer. In cities, one transformer may supply 50 to 1,000 consumers. In rural areas, one transformer may supply only 1 to 10 consumers. This affects transformer rating. In urban networks, typical transformers rating range from 300 kWA to 1,600 kWA. In rural networks, transformers rating are often between 16 kWA and 50 kWA. Next, let's examine how low voltage feeders length are. In cities, low voltage feeders are short, typically less than 300 meters. In rural areas, low voltage feeders may reach 500 to 1 kilometer. This influences voltage drop and losses. Line type is also different. In urban networks, mainly use underground cable lines. In rural networks, often overhead lines. Conductor cross-section reflects loads levels. In the cities, aluminum conductor cross-section range from 120 square millimeters to 400. In rural areas, typically cross-section range from 16 to 50. Urban medium voltage networks often operate as part of the ring or open mesh system. This increases reliability and allows load transfer between feeders. Rural networks are typically radial. This reduces investment cost but limits flexibility. Let us look at the practical examples. In the city district, a 20 kilowatt cable ring connects several compact substations. Each substation has 630 up to 1000 kWA transformers. Low voltage feeders are short and supply apartment buildings or commercial centers. If a cable fault occurs, only one section is isolated and the supply is restored from the opposite side. In the village, a 10 kilowatt overhead line runs several kilometers pole mounted. Substations are 25 or 50 kilowatt transformers. Low voltage line extend from each transformers to nearby buildings. If a fault occurs, a large area may lose supply until switching or repair is completed. From an engineering standpoint, urban networks require higher short circuit withstand capabilities, more advanced protection coordination, and more switching points. Rural networks require long-distance voltage top control, careful conductor sizing. You must always match network structure, load density, and consumer patterns. Urban design focuses on reliability. Rural design focuses on economy and long-distance supply. Both systems serve the same purpose, but their technical parameters and configuration are fundamentally different. Now we look at the medium voltage network in the sparsely populated region. The diagram shows a typical structure. At the top level, a 110 kilowatt transmission line supplies the region. A 110 to 20 kilowatts primary substation transforms voltage down to 20 kilowatts. From this substation, 20 kilowatts feeders spread across the area. Along these feeders, many 20 to 0.4 kilowatts distribution substations are placed. Each distribution substation supplies local low voltage consumer through the 0.4 kilowatt networks. The scale bar shows about 10 kilometers. This highlights the key features of the rural system. Distances are long, consumers are dispersed, feeder branching is extensive. In such regions, reliability is usually lower than in the cities. The main reason is simple. Rural networks often lack reserve paths. Many feeders are radial and long. If a fault happens on the feeder, consumers downstream lose supply until switching or repair is completed. In the city, networks often use open ring or open mesh structure. This provides alternative supply paths. Outages are short because operators can isolate the faulty and resupply from other direction. In rural areas, this is harder. Feeder interconnections are fewer. Switching points may be farther apart. Automation is less common. Now consider typical faulty cause. In the city, the most common fault occurs in cable networks. Cable damage can happen due to excavation, isolation failure, or faults inside distribution substations. These faults often lead to short outage because the damaged section is limited and quickly isolated. In rural areas, most lines are overhead. The most common cause fault is weather. Strong wind, heavy snow, ice loading, and falling trees can damage overhead conductors. This can create long outage. Repair crew may need hours to locate the faulty and restore the lines, especially in the remote areas. This explains a key operation difference. In the cities, interruptions are usually short. In rural regions, interruptions can last hours, sometimes longer. Now link this to the engineering design. If you design a sparse area network, you focus on cost control, long distance voltage drop, reliability overhead line construction, strategic placement of switching points. If you want to improve reliability, you add more feeders, interconnection, more sectionizing switchings, remote control, and so on. However, every upgrade increases cost. This is why rural networks are often designed with a simpler configuration. One more point from the diagram: the number of spacing of 20 to 0.0 kilowatt substations reflects low load density. If you install many small substations to keep low voltage line short and voltage equally acceptable, this matches the Estonian practice of limiting low voltage feeder length, so the configuration represents the common rural logic. Strong 110 kilowatt backbone, one of few 0 to 20 kilowatt substation, long 20 kilowatts feeders, many small 20 to 0.4 kilowatt substation, short local low voltage networks. This is the standard model of electricity supplying in separate population regions. Now we look at medium voltage network connections, the high voltage transmission system with the low voltage consumers. Electricity flows from power plant, high voltage to 110 kilowatts transmissions, primary substations, medium voltage, distribution substations, and final consumers. About half of total electricity cost is linked to distribution. For this reason, network structure must balance reliability and investment. Network configuration types. Medium voltage networks can be radial, open ring, meshed, and so on. Radial networks are simple and low cost. A single fault disconnects downstream consumers. Ring networks provide alternative supply paths. They usually operate open to keep protection simple. Mesh networks offer higher reliability but require complex protection and higher investment. In practice, most medium voltage systems operate radially as a part of open rings. Busbar and feeder structures, primary substations may use single busbar, tube busbar with a bus coupler. In two-section system, each transformer supplies its own busbar. If one fails, reserve automation connection both sections. Feeders often form rings with one normally open point. If a fault occurs, the faulty section is isolated. The open point is closed. Healthy sections are resupplied. This structure provides fast restoration without full mesh complexity. Feeder branching and sectionizing medium voltage feeders may contain multiple branches. Branching point uses load breaker switches or disconnections. This allows fault isolation, maintenance without total shutdown. Load transfer between feeders. Feeder interconnection increases operation flexibility. Two feeder schema allows supply from different substations. Protection remains mostly radial at any given time, which keeps coordination manageable. Urban versus rural networks. Urban networks load density above 1 MW per square kilometers, 50 to 1000 consumers per transformer. Transformer rating 300 to 1600 kVA. Low voltage feeders length below 300 meters. Underground cables, open ring configuration are also common. In rural networks, low density below 100 kW per square kilometer, 1 to 10 consumers per transformer. Transformer rating 16 to 50 kVA. The low voltage feeder length 500 to 1000 meters. Overhead lines are usually common. The radial configuration is typical, and urban system focus on reliability and power quality. Rural system focus on cost-effective and long-distance supply. The voltage levels and distribution strategy common medium voltage level include 6, 10, 15, 20 and 35 kV. Extending distribution more on medium voltage results in short, lower voltage feeders. Lower losses, better voltage quality, and so on. In Estonia, low voltage feeders length is typically limited to about 600 meters. Reliability and automation supply reliability depends on network topology, feeders, and other things. There is no universal best configuration. Higher reliability increases cost and protection complexity. Your task as engineer is to match configuration to the load density, define normal and emergency switching states, coordinate protection for all operation conditions, ensure equipment rating, supply reserve, and so on. Thank you for watching, and see you next time.